Eugene, are your Z and X's flipped there?
No, it's not. Because this is X, this is X is along the axis. But because I'm viewing from the bottom, Adam, right? That's why Z is going down this way. Here is
Oh,
where my eye is.
yeah, okay. It's
Okay.
just the Z in like the main picture goes like back up.
Yeah, but because I'm looking from the bottom, right? So I'm at the bottom of the shaft now, Adam.
Yeah, yeah. I just thought the Z arrow should go up the page. That's all, but that's fine. Yep.
Is that okay? Is that right? You have to be convinced it's right first.
Yeah, yeah, that's right.
Okay. So when that's the case, so when that's the case, right? So if you look at the torque, so this is the direction of the torque. Or this is known as torque in the x direction. Okay. So when that's the case, if you lock this end up, right, this point will want to move over here. I mean, this is exaggerated. You want to deform over there. And with that deformation, you have a shear looking like this. Okay. So when this is the case, right, when this is the case, right, if we look at our element now, right, so I'm going to draw this as positive shear. And then I'm going to draw this. Sorry, that is negative shear. I do apologize. And then this is positive shear. Right? So if we look at our element now, our element is under what? Negative shear. Okay, this is our element C. Why? Because the shear, the torque is going up that direction. Okay. So now, if we were to draw the entire element now, okay, if we were to draw the entire element now, okay, so if this is my Z, this is my X, okay, so if we were to draw it now, we know that our element will look like this, okay, so this is my stress in X will be in compression, and then my shear will be negative shear. So this will be my shear XZ is equal to shear ZX. Okay. So this is how our element will look like during deformation. So you have both a compression and a what? And a shear. So some of you might say, Eugene, can you draw this in 3D? Okay. So if I'm going to follow, now, before I go on, I know some of you like, this is so late to be teaching this. Am I right? Okay. Yes, you are absolutely right. Okay. This is only critical when we design structures that uses material, okay, uses material like carbon fiber. Remember, you guys did 3C with me, right? Is only critical when it's carbon fiber. When it's not carbon fiber or ductile material, does not matter. Okay, because it only switches the point of X and Y on Mohs circle, which I will not be giving you marks for it. If you got it the other way for this sort of problem, I'm not going to give you extra marks or deduct any marks because it's the amplitude that's critical down here, not the direction. Okay. But some of you might be curious, Eugene, I want to know how does the Mohs circle look like. Okay. So if I'm going to follow the transformation over here, okay, I'm going to follow the transformation over here. Okay. Some of you will say, Eugene, that's why they use software for this. Yeah, but those software are too expensive, okay? So now element C will look like this now. All right? So we know that there's a normal stress in compression over here. And then we know that there's a shear, right? There's a shear component doing this. Okay. So that is how our shear will look like. Okay. So this is our point X, right? This will be our point Z, all right? And then the hidden feature over here. Okay. This surface over here, which I'm going to use dotted line, this is our point Y, which is at the bottom plane. Okay, this is at the bottom plane. Okay, so from here we are going to sketch out mole circle, just a sketch. Okay, to visualize where are we on mole circle in this structure. Okay, just a sketch. Okay, why we need to sketch? Because we have to know whether is the maximum shearing stress in plane or out of plane. Okay, if we get it wrong, oh, it's not going to be funny. Okay, so we're going to sketch this now. Okay, so we know that over here, right, we know that stress Y. Okay, so we know that stress Y is definitely equal to 0. There's no normal stress. Okay, so now we sketch mole circle. Again, as I said, this is just a sketch. So normal stress, then we have our shearing stress, clockwise, anti-clockwise. Okay, we know point Y will be over here. Okay, we know point Y will be over here. We know that. Okay, we know point Y is. Then I don't know what's the shear value. It's just a sketch. Okay, I need to visualize just a sketch. So this is my sketch. Okay, and this is my sketch. Oh, I'll bring it closer, easier for me to draw. Right? Okay, so over here, we know that stress X has a compression. Okay, so we know that this is our stress X line. Okay, we know this is our stress X line. Right? We are aware of that. That is our stress X line. Okay, so if we look at stress X now, okay, if we put our finger at the center, right? We put our finger at the center. The element will rotate clockwise, right? So this is my point X, and this is my point Y. The element will rotate in a clockwise direction. So this is point X. And we know that over here, this is my point Y. Point Z, yes or no? Right? So once we have this, we more or less know what is the big circle. Now, I want to highlight to you, right? Do not worry about your shear. Okay, do not worry about which direction is this, unless it's carbon fiber. Why? Okay, so now let's say if you got it opposite, okay, if you got it opposite, so you call this X, you call this Z, right? No, not like that. Sorry, the other way. Sorry. So now if you got it opposite, okay, let me say what is it opposite. So now, okay, because of time, Eugene did not teach us properly, right? Which is true. And then you happen to flip this. Now what will happen if you call this one X and you call this one Z? What will happen? Nothing. Why nothing? The diameter of the circle is still the what? Still the same. Okay. So now if I were to draw 2.5 and 2, hold on, I'm going to draw more circle first. Squared plus 2 squared. So it's 3.2. Okay. So the center of the circle is somewhere around here. Right, so I'm going to sketch mole circle. Okay, so 1, 2, 3 and a bit, 3 and 3.2. So this is your mole circle. Okay, I think I'm a bit too plumb for the circle. Okay, so this is our first circle, right? So this is our exact plane. right? This one is for our XZ plane. And then we have to construct the other two circles. So one circle will be over here, right? All right, this one will be known as our YZ plane. And then there's another circle, 2, 4, 2, 4, 4 and a bit. Okay, then there's another circle over here. Right? Not really a very good circle, but bear with me. So this circle over here is for your what? Is for your YZ plane. So from here, what you realize that you will know where is your what? Your maximum is where? Your maximum is on your XZ plane. And your XZ plane is your what? In plane. When it's in plane, you can apply what? That's where you can say, hey, I can apply 2D mole circle. Right? Because why? Because this surface over here is your XZ plane, and your XZ plane is your what? Is your in plane. Okay, so you no need to you no need to worry, but you still need to use mole circle to verify. Okay, you still need mole circle to verify. So remember what I told you, right? Whether you get the XZ, so this is the correct value. If you flip it the other way, your circle diameter will not change. Okay, so do not worry. Okay, currently there are 2 YZ. What do you mean there are 2 YZ? Did I label 2 YZ? Oh, you are right. There are 2 YZ. Okay, so that is YZ. Okay, and then this one is XY. Sorry, you're right. Okay, XY plane. Okay, so the exact plane is the one that has the what? So now we know that this is the what? Tau max. Okay, so now once you know the tau max, right? So you can say that tau max, the formula to use for tau max is equal to normal stress max now minus by normal stress mean divided by what? Divided by 2. Okay, so from here, I'm so short of time. I have another page to write. The longest I'll go is 4:30. Okay, because the rest is math already. Okay, so from here we are going to consider the big circle now. We're going to consider this big circle. We're going to consider the bigger circle, and the bigger circle is from your what? Is from your X point and your Z point, and the X point and Z point. Okay, so this is not Y. Okay, this is your Z point. Okay, is here and here. So you can use this circle. You can use this element on its own. Okay, so now the next thing is, what are our stress X and what is our shear XZ values. Okay, so we're going to calculate our stress X first. Okay, I'm going to calculate our stress X. So determine okay, we're going to determine our stress X value. Okay, so this is where this is the simple part. Okay, so due to axial loading, okay, due to axial loading, so stress X is equal to minus 2,500, okay, over pi c squared, where c is the radius, okay, is the radius of the shaft. Okay, and then due to bending, right, and we know it's under compression. Okay, we know this under. Then due to bending moment, okay, again stress X is equal to minus MC over I, right? C is the biggest radius, right?